Okay, so we will start from our previous topic, and that is nothing but audio power amplifier. Yesterday we discussed about the basic block diagram of that audio amplifier and about the power amplifier, that is last block, right? So we'll see today. I will use the PowerPoint because so many diagrams are there. I will share my screen. Am I audible properly?
Yes.
Yes, sir.
Okay. My screen is visible.
Yes, sir.
Okay. So see, yesterday also we discussed about these 3 points. Power amplifiers, functional blocks of that amplifier consist of um, main block, that is nothing but power supply. Basically, we were going on to use the mains power supply, and that is 230 volt RMS that we can convert to the required DC for that amplifier or various stages. Then there is one input stage, output stage. One more yesterday, I told that is nothing but driver stage or that volume and tone control and all that, right? So the power supply, already I told, we will move on to prefer to 30 volt AC and the required DC will be going on to convert by using that rectifier and all that, right? Regulators and all that. Then the input stage, yesterday I told about that pre-amplifier, right? So that is nothing but the actual input stage. So you might be familiar with this balance input and single-ended input. Balance input means what? See, the example is like dual input balance output differential amplifier, and that is the input stage of OPAMP, right now. So that pre-amplifier basically it is designed to process the very weak signals. Okay, sufficient amplification is also done by using that input stage. So mostly balance input stage is preferred to have the proper amplification, as well as we can say to improve the parameters of that amplifier circuit, overall parameters like its input impedance, then noise rejection, etc. Right? And single-ended input means our conventional amplifier circuit. Anyone you can consider like BJT amplifier or MOSFET amplifier, where uh, single terminal is there or single input signal we can apply to it, right? So see here I mentioned that balanced inputs are much more preferred over the single-ended inputs when interconnection cables are long and are subjected to noisy electrical environments because they provide very good noise rejection, right now. So this is a feature of that balanced input stage. That is nothing but dual input balance output differential amplifier that you might have studied in your integrated circuits, right? Dual input and balance output means what? In that differential amplifier, there are two inputs and the output is taken out from the collector of both transistor. If you can recall that circuit diagram, that is dual input balance output differential amplifier, then you will get clear about this, right? So the feature of that dual input balance output differential amplifier is its good noise rejection ratio, and mostly uh, we have to prefer it if that interconnection between cables and that cables means what, the actual mic, right now, that is the input signal source and the input terminal of our power amplifier or the input stage of our power amplifier. Okay, so if there is a somewhat or much more distance, as well as if there is a noisy electrical environment, we can say, then mostly these balance inputs are preferred. Then the output stage, yesterday already we discussed on this one, the portion which actually converts the weak input signal into a much more powerful replica. See, much more powerful means what? You have to consider it in terms of current. Okay, voltage amplification, it is basically done by the previous stages, like that driver stage or pre-amplifier and all that. Or we can add number of stages if we require much more voltage amplification. But the main thing is what yesterday also I explained. The main thing is to drive the low resistive load like a speakers. Okay. Yesterday again I told that speaker resistance, it is mostly 4 to just 8 ohms. And that's why it works as good as short circuited. Not short circuited, but as good as short circuited. Why I am saying as good as short circuited? Because as the resistance is very low, the amount of flow of current through that load or the current consumed by that load, it is very high. And hence that last stage, that is our amplifier stage, it takes the care. That means instead of we can say not only voltage amplification, the care by this last stage is taken about the power amplification. That means overall power gets improved right now. Then amplifier classes yesterday already we discussed. Now we'll see the various circuit diagrams, how they can be used. Now see, as shown over here, this is the basic circuit diagram for that output stage. After diploma students might be familiar with this one. Such type of combination is known as a push-pull. Okay, how it or why that name is given as a push-pull, that also later on I will be going to explain. But the feature of this circuitry is it improves the current rating of that amplifier. Right? Two transistors are connected. One is N channel, another one is P channel. If they are replaced by BJT, then the first one towards the positive DC source, that transistor, it should get replaced by NPN transistor, and the bottom side it should get replaced by PNP transistor, right? And how it works, or what problem occurs with such basic circuits, that also we will going on to discuss in the next PPTs. Then I will go on to show two circuit diagrams. That screenshot, you have to take the screenshot during our next practical in the next week. We will going on to implement that and we'll try to obtain the results. Okay. And that will be our practical activity for our journal. Okay. So see, looking towards these waveforms, the discussion already yesterday we done related to class A, class B, class AB and class C. Okay. So this first one, as it indicates that collector current, it never goes to zero. If you look it properly, you will observe that current waveform, it remains in the first quadrant only, right? That means there is no negative component for that collector current. Only the magnitude of that collector current, it gets varied. It indicates that the transistor is biased at the center of load line, right? Is it okay? Are you agree with this?
Yes, sir.
See that first collector current waveform, don't consider this dotted line as the x-axis. Huh? X-axis is actually this one, right? So that collector current, we can't call it as a AC current. Huh? Remember, it is not alternating, it is time varying. Okay, because that current never goes to zero, or it consists of only positive values. Only its magnitude it gets changed. Okay. Now see, but in general we are calling the, or we are considering the output of such type of amplifier as a AC output. Correct. So how it will be possible? It is possible only by using that output coupling capacitor. See, at pi, at an angle of pi out 2 pi or even at 3 pi, you will observe that signal, it becomes DC signal. Correct? Because just imagine when the input signal, yesterday I drawn that DC load line, all that, when input signal starts from 0 or comes again back to 0 at pi or 2 pi, how much is the value of collector current? It is ICQ, quiescent collector current. And quiescent collector current means what? It is a DC component, right? So at pi or 2 pi, as the output coupling capacitor is connected in series with the load and collector terminal or the drain terminal of BJT or MOSFET respectively, that coupling capacitor, it blocks the DC components and hence the output is 0. But later on, that component again becomes time varying. So that capacitor again provides the output. That's why we are getting that output somewhat like a AC signal. Okay. Now in second waveform, you will observe only the obtained output is 0 to pi or 2 pi to 3 pi. That means only positive half cycles are processed. There is no negative half. Means for the time period pi to 2 pi, that transistor, it remains off. That's why we are not getting the output. Correct? Or not getting output, it is not like that. Here, the shown waveforms are collector current waveforms. So from pi to 2 pi, as transistor enters into the cutoff region, because that transistor is biased exactly on the x-axis. Just recall our previous discussion that transistor is biased exactly at the on the x-axis on the DC load line. During positive half of input, that Q point, it gets shift from cutoff region to its either saturation region or active region for MOSFET or BJT respectively, right now. So during the positive half of input, transistor remains in conduction. But when the input signal starts to increase negatively, that means pi to 2 pi, during that period, the transistor remains into the cutoff region and hence it remains off as open, we can say, and that's why current flowing, that is collector current, through that transistor, it remains 0. Right? And such type of amplifier, we classified it as a class B. So this first one is for class A, collector current waveform for class A. Second one is for class B. Am I right? Now see, for next one, that is class C. Okay. The transistor is biased somewhat below the x-axis. See, during positive half of input, again we are not getting that complete positive at the output. Means collector current completely during the positive half. You will observe between 0 to pi, see, there is somewhat time difference. And later on, we can obtain the current waveform. Is it? Again it goes to 0 before angle pi. Is it? That means the conduction of transistor, it is less than 180 degree. In second case, it was perfectly 180 degree. In first case, it was 360 degree. But in third case, that means for this class of amplifier, that is class C, the conduction angle of the transistor, it is less than 180 degree. Right? Then switch to the last one. You will observe transistor, it conducts during first positive half cycle as it is, completely, we can say. Similarly, partially to negative half. Right? Can you observe it properly on your mobile? See, the
Yes,
conduction angle of transistor, it is somewhat greater than 180 degree, but less than 360. It indicates what? The conduction angle is greater than 180 and less than 360, and that's why we classified it as a class AB. That is between class A and class B. Class A means at the center, class B means on the x-axis, and that's why class AB, it means between center and the x-axis. Not exactly at the center, not exactly on the x-axis. Right now. And we correlated it because of such type of conduction, we correlated it to its power dissipation as well as the efficiency. Right now. So for class A, yesterday I told that efficiency obtained as the transistor remains continuously in conduction, there is continuous power dissipation and it affects the efficiency of that amplifier. So efficiency for class A, it is almost 25% and we can improve it maximum up to 50% by using few modifications. After diploma students might be known, they might have studied about transformer couple class A power amplifier right now. So if transformer coupling is done with the basic class A amplifier, then that efficiency gets improved to 50%. There is one derivation how that efficiency gets improved to 50%, right? Then for class B, as the conduction is only for 180 degree, I think yesterday I mentioned that efficiency almost at the closer to 75%. I think it is 78 something. Okay. Again, there is derivation for that class B also, but it is not there in your syllabus. Only as a general knowledge, you should be familiar with that, and that's why that efficiency of that class B, it is almost up to 78%, as the conduction angle is less than 360, as it is 180 degrees. Then for class C, yesterday also I told its efficiency will be maximum because the conduction angle is minimum, and hence the power dissipation will be minimum. And for class AB, it will be between 50 to 75%. Okay, class A output stage is a simple linear current amplifier. It is also very inefficient, typical maximum efficiency. See, here it is mentioned as a 10 to 20%, but as per derivation, uh, we can observe it as a 25%, but what is mentioned over here, that is 10 to 20, it is a practical one. By considering another losses, it is not considered within that derivation part. So it is derived as a 25%. So that class A, it is only suitable for low power applications. High power requires much more better efficiency from that amplifier circuit or from that power amplifier. So class A output stage. Basically, that output stage can be designed and developed by using class A configuration. You will observe there are two transistors. Out of that, the lower one is working as a constant current source for the first transistor, and that first transistor is in we can say emitter follower configuration, because the output is taken from emitter terminal of that Q1, and V1 is nothing but, we can say, the signal processed by the previous stages. It is applied as a input signal to transistor Q1, and that transistor Q2, it is used as a constant current source biasing to operate that transistor in the respective region. That means at the center of that load line, right? So these are the basic diagrams, not the final one. Then the transfer characteristic, as the transistor conducts in or during both half cycles, so that we can say it will be able to conduct in first quadrant as well as in third quadrant, because that current, it also gets reverse right now, because the input signal is positive as well as negative half cycles, and as the conduction takes place during both half cycle, means we can say the transfer characteristic, it lies between first and third quadrant. And this waveform already I shown in the previous one only, so no need to again explain it. The shown IC, it is IC peak. Okay, so see here, the purpose of this PPT is only to show you about the phase shift between input and output. Output, it looks somewhat amplified by applying the input of somewhat low amplitude, but there is 180-degree phase shift. In case of common emitter configuration for BJT, there is 180-degree phase shift. It provides somewhat better voltage amplification. Similarly, in case of MOSFET, for which configuration there is 180-degree phase shift, that is common source configuration. Okay, and for remaining two, that is for BJT as CB and CC, there is no phase shift, or we can say 0-degree phase shift between input and output, but CB configuration, the voltage amplification much more poor, as well as in case of CC configuration, the maximum voltage amplification is unity, but its advantage is about the current amplification. It provides very large current amplification. Okay. Similarly, same is applicable for MOSFET also. So the shown diagram, this is for either CE or CS, that is for BJT or MOSFET respectively. Now just take the screenshot of this circuit diagram at your end. The same we have to implement during our practical session, and we'll be able to check the output. Is it really working or not? I also don't know, because I have not tried it from my side. So we'll be able to check it actually during our practical session. We have to check that transistors are available in our protis or not. If it is not there, then we will be able to try to obtain by using Google its equivalent 2N3904. Okay. So you will observe in this circuit diagram, the first stage, this is nothing but C amplifier, a simple C amplifier, right? And looking towards it, or by taking the actual results, we have to justify that transistor or the shown amplifier, this first stage only up to capacitor C3, output coupling capacitor, is it working as a class A or class B, class C or class AB? Okay. So whenever we will want to implement it in our protease, how we can justify the shown first stage is for class A or class B or class AB or class C? Can anyone? Whatever the things you studied in your EDC, apply that logic. Whatever you studied in EDC, looking toward this first stage, can you identify the shown first stage amplifier circuit is either class A or class B or AB or C? Can anyone? Just try it. It's very simple how to identify that type. Okay, no one? Okay. So see, initially what we will do, we're going to implement only DC equivalent circuit for the shown amplifier, right? So what you will do, or how that DC equivalent circuit is to be drawn or implemented? You've done that analysis already for CS MOSFET amplifier in EDC. Same logic you have to apply over here also. Only the difference is instead of MOSFET, BJT is used. Remaining logics considerations are same. Can anyone? Just consider up to C3 from VS signal source to capacitor, output coupling capacitor of that first stage, that is C3. Am I audible?
Yes, sir.
Okay. Just consider that circuit diagram from signal source, that is input signal source to C3. Here,
So for the DC analysis, the
yes,
capacitor will be of no use. Then the power supply will be shorted.
for DC analysis,
Yeah.
DC power supply is to be get shorted for AC analysis, not for DC, right now.
So, yeah, yeah,
Huh. And all capacitors act as a open circuited, right?
yeah,
As we are thinking about DC analysis, means only DC components, we are considering that all capacitors, as they are connected, somewhat like that capacitor C1 and C3, it looks like in series, they will be going to act as open circuit for DC components, right now, as they will be going to provide the reactance as infinite, 1 upon 2 pi Fc, is it? So as F is the zero, that means as we are considering only DC components, the reactance provided by the all capacitors, it will be infinite, and that's why in general we are seeing for DC analysis all capacitor acts as a open circuit, right? So there will be only resistor R1, R2, then resistor RE1 and RE2. Okay, because this bypass capacitor 100 microfarad C2, it will act as open circuited. So only two resistors will be there, that is RE1 and RE2 in series, and RC again as it is, that is 1K, and it will be powered by plus 15 volts, right? No input signal, no input coupling capacitor, because that capacitor will act as open, and that's why this input signal source, it will get disconnected from the DC equivalent. Okay, and there will be a node, this is most important, between base terminal and the voltage divider formed by R1 and R2, right? Now the question is how we can check the transistor is either biased as a class A, class B, class AB or class C. Can anyone? Okay. Just consider a DC load line in the first quadrant, which yesterday we already discussed. There is a crossing point or maximum level of that DC load line on y-axis as what? VCC by RC, right? To that point, it will be VCC here, it is considered as a 15 volt, RC is considered as a 1K, that means the point on the y-axis, it will be 15 milliamperes. Got it? Because that y-axis is for collector current, right now. And how much maximum collector current will be there? It will get decided by resistor RC. That is the purpose of resistor RC, to limit the collector current, right now. So it will be 15 milliamperes, because that maximum level of DC load line on the y-axis is VCC by RC, that point, or we can call it as a IC max. So in this case, IC max, it will be VCC by RC, that is 15 volt divided by 1K. So the answer will be 15 milliamperes. Am I right? Is it okay?
Yes.
Okay.
Yes.
Now that DC load line will be going to take crossover on the y-axis, and that point generally we are saying VCE max equals to what? VCC. So on y-axis it will be at 15 volts, and we will want to prefer this 15 volts right now. So that DC load line, it will be in between 15 volt, and on y-axis it will be 15 milliamperes. Is it okay? If possible, at your end, just take the notebook and pen and draw that DC load line and indicate these two as a maximum point. Okay. Now we have to locate that operating point practically. So see, if we just consider that operating point is exactly set at the center of DC load line. Okay. Just draw it at your end. Consider that operating point is located exactly at the center. Now, from there, just try to plot the voltage level on x-axis. That is for VCE. How much it will be?
Half.
Yes, it is exactly half of VCC, and that is nothing but 7.5 volts expected. Am I right? Now,
Yes, sir.
now if suppose that operating point is selected below the center and above x-axis, somewhere below the center and above the x-axis on that DC load line. So just take the second consideration, that operating point is selected below the center and above the x-axis. Okay, and just try to find out how much will be VCE on x-axis. So here I can say the obtained VCE, it will be greater than 7.5 and less than 15 volts. Are you agree with this?
Yes, sir.
Okay. Now consider the next case, if that operating point is located above the center, just above the center, but below the IC max, and try to locate that VCE on x-axis. Here,
Less than 7 point.
yes, it will be greater than 0 volt and less than 7.5. Is it okay? Now, it's very simple. Just implement all these components, R1, R2, RC, RE1, RE2 and transistor. That's all. Power it by 15 volt. Take the DC voltmeter and connect it across collector and emitter. Not at the ground. Huh? See, that voltmeter, it should get connected to the collector with respect to emitter terminal. Don't connect it, that means the negative of that voltmeter to the ground. Otherwise, that voltmeter will going on to measure the voltage drop across RE1, RE2 and across collector to emitter. So it will show the combined voltage drop. We are interested in what? Where the transistor is biased. That means we have to note down how much is the exactly VCE. So for the shown circuit, if on that voltmeter, exactly if we got that VC equals to 7.5, then what we have to say? The transistor is biased exactly at the center, right? And the shown amplifier circuit is working as a class A power amplifier. Are you agree? Is it okay?
Yes, sir.
Yes, sir.
Okay. If you got the value across collector to emitter of the same transistor equals to 15 volt, then what is the meaning?
It is a class B.
Yes, very nice. Then we have to say the shown transistor is working as a class B or shown amplifier is working as a class B power amplifier, right? Next, if the voltage drop across collector to emitter is greater than 7.5 and less than 15, that means it is working as a class AB. So simple, right? Now remember, whenever that transistor is operating below the x-axis, then we are calling it as a class C, but over here we can't identify it. If we got that VC as a 15, then there will be two options. Either that transistor is working as a class B power amplifier or it is working as a class C amplifier. Because if it is biased below the x-axis, still it will remain in cutoff region and hence we will get the voltage drop equals to 15 volts or voltage across that transistor as a 15 volts. So between class B and class C, it is somewhat difficult to identify. It will be possible only when we will go on to observe the input and output signal waveforms. Is it correct?
Yes, sir.
Okay. Now, once we will identify it, later on, we'll apply the input signal, that is 500 millivolt peak to peak. Over here, it is shown with the frequency that is within audio range. It is taken as a 1 kilohertz, right? And at the output of that complete amplifier now, first stage, we'll check the input and output signal waveforms. And we'll go on to identify the first and main parameter, AC parameter, and that is nothing but voltage gain, right? And you can easily determine it because the remaining procedure is very simple. Just connect the CRO to the output, apply 500 millivolt 1 kilohertz from the function generator, connect the second channel to the input side just to compare the input and output signal waveforms, note down peak to peak amplitude of the obtained output and the applied input. Applied input is 500 millivolt peak to peak, obtained output is how much, that practically we will check and we'll go on to decide how much is the gain of this first stage. Is it okay? Now, second test, is it working as a pre-amplifier or is it working as a conventional amplifier? That we have to identify. Okay, so what we will do, we'll go on to decrease the input signal amplitude below 500 millivolt. Parallelly, we will go on to check that amplifier is still providing amplification with the same gain or not. See, gain gets differ by change in frequency, not by change in amplitude. Okay. When we will decrease that input signal amplitude at a particular stage or at a somewhat amplitude of that input and below it, we will observe that amplifier circuit is not working as an amplifier. That means output becomes noisy, corrupted. Right? So for example, if this first stage do not support 100 millivolt peak to peak signal. Okay, this amplifier do not support 100 millivolt peak to peak or below 100 and below 100 millivolt. Above 100 millivolt, we are getting the output. So we will call it as a conventional amplifier, right? Now, as it will not going on to support, just I taken that example, actual how much that we will practically identify it. Okay, suppose it is 100 millivolt peak to peak that do not get processed by this first stage. Then what to do? Now we will go on to design and develop another amplifier by using another devices just like OPAMP. You already studied OPAMP as inverting amplifier, non-inverting amplifier. Over here, as it is in C configuration, so we are calling it as an inverting amplifier because just in previous slide I shown there is 180-degree phase shift between input and output right now. So we'll try to configure the same amplifier, that is inverting amplifier, by using OPAMP. And over there, we'll set the gain of that amplifier in such a way that it can process that 100 milli or below 100 milli. And you are already familiar, the gain of inverting amplifier is simply, it is dependent on externally connected feedback resistor and the input resistor, that is RF and R1. So for inverting amplifier, the gain is minus RF by R1, is it? So to have the same gain, that means, see, for this amplifier, whenever it processes the 500 millivolt peak to peak signal, for example, if we got the output as 5 volt peak to peak, we can calculate the gain, right? For this basic amplifier, same gain we can set by using OPAMP in its inverting configuration, and the signal which this amplifier cannot process, the same signal we will observe that OPAMP can process, or below than that of. The example we taken it as 100 millivolt, but that OPAMP can easily process it. So we will call that OPAMP as a pre-amplifier, and this one as what? Conventional amplifier. Is it okay? Are you got it?
Yes, sir.
Okay. So practically we will be going to check it. Don't worry, right? During practical session, I will be going to explain it again. Now, the next stage, that is actually it is the output driver stage. You will observe that such type of connection is known as a Darlington connection. The output of first transistor, that is emitter terminal, it is connected to the input or base terminal of second transistor. Second means over here it is Q3. Output of Q2, it is directly given as the input of Q3, and collector terminals of both transistors are commonly powered or connected with each other and commonly powered. So such type of connection is known as a Darlington connection. Transistor Q2, again it is biased by using resistor R3 and R4. That means by using voltage divider to have somewhat VBE greater than 0.7. If the transistor is to be biased at the center, right? Now, accordingly, the values of R3 and R4 are selected. So here we will consider that transistor Q2, it is biased exactly at the center of load line, and accordingly the resistors R3 and R4 are selected. Or over here also we can easily identify where the transistor Q2 is biased by the same procedure. We'll remove that capacitor C3, we'll turn on the power supply, and across Q2, that is its collector with respect to emitter, we will be able to measure the voltage by using DML. If it reads that voltage at 7.5, then we can say that transistor Q2, it is biased exactly at the center of load line. And same thing we can do for Q3 also. Right. Now see, what is the feature of this Darlington pair? It is known as a Darlington pair or Darlington connection. Okay. Its feature is it provides current amplification. The voltage amplification is not that much measurable, but current amplification is very high. That is the feature of Darlington pair. Okay. And as per our previous discussion, we require the same from the last stage or output stage, or it is also known as output driver stage, or it is also known as a power amplifier. Okay. So this last stage will take care about the current amplification. And as it is in emitter follower configuration, that means output is taken out from emitter terminal, you will observe it is directly connected to that speaker, which is of 16 ohm only. Right. One more resistor is shown over here, 16 ohm, 2 watt. This is for the biasing purpose of that transistor Q3. But its wattage is shown very high, that is 2 watt. Just imagine 2 watt resistor. Why it is taken as a 2 watt? Because already I told the last stage it provides a very high current amplification. So the emitter current of Q3, it will be very, very high. So if the selected RE3 16 ohm, if it is of low watt, then in hardware actually you will observe that resistor gets damaged because of overpower dissipation beyond its power handling capacity, and that's why it is mentioned that resistor RE3 is of 2 watt, and speakers are already, it is very high wattage device. Okay, it can handle a very high current as well as power dissipation. As it is shown, just 16 ohm, that means it will be going to consume a sufficiently large current. Capacitor C4, it is used to block the DC components coming from VCC through transistor Q3 towards the speaker. Otherwise, there will be a noise. DC signal will get mixed with the AC amplified components. Is it okay? So I got this circuit diagram as a basic audio amplifier. So we'll try to work out on the cell. Are you taking the screenshot?
Yes, sir.
Okay, so before our practical session also in the next week, you can try it at your end. Okay. Then few benefits and all that are mentioned, like class A benefits: no crossover distortion, no switching distortion. Switching distortion means what? That transistor will not going on to switch between its on and off region. Okay, as it will be going to continuously remain in its amplifier region. Why I am saying amplifier? Because if BJT is considered, then that amplification region is known as active region. If MOSFET is considered, then it is known as a saturation region. Okay, so commonly I said in its amplification region. So as that transistor continuously remains within that region, the switching of transistor do not occur. Switching means what? It never gets turn on. That means turn on and turn off. That action do not take place. It will be going to take place if it is a class B or even class AB or class C. Just imagine. Okay. So see, if it is class B, it is configured as a class B amplifier, then the operating point will be on the x-axis. Okay. During positive half, transistor will get turned on, and whenever there will be negative half of input, transistor will get turned off. Okay. So turn on and turn off action will going on to take place if it is in class B configuration. Even in class AB also, partially it will going on to remain on during negative half, but partially during negative half it gets turned off. That means turn on and turn off action takes place in case of class AB also. And you are already familiar with class C. Over there also it will going on to turn on for a very small time duration and will remain off for a long time duration. That means the conduction angle is as it is less than 180 degree. That means excluding class A, there is a switching action, and that's why some distortions gets added. So what is the benefit of class A? No switching distortion. Okay. Low harmonic distortion in the voltage amplifier, lower harmonic distortions in current amplifier if that class A it is configured either as a voltage amplifier or even current amplifier. So the harmonic distortions are less. Then no signal dependent distortion from the power supply, constant and low output impedance. This is most important. See, whenever we are considering to power the high load means not in terms of load resistance, high load means in terms of their current requirement. Okay. So if that loads are high power loads, that means low resistive load, then the output impedance of voltage amplifier, it should be as low as possible. Ideally it is, generally we are saying ideally it is 0 ohm, so that the maximum power gets transformed from amplifier to load. Okay, so that class A it provides somewhat low output impedance, so it is in that consideration it is best. And last one is the simpler design. Then next slide is the comparison between class A and class B. So I think our time is also over. So the remaining slides we will go on to continue from the next lecture. Okay.